Very good morning. Today, I will discuss the very basic details of Finfet, and that concept was already shared with you via some notes, some PDF as a PDF format. But today I will let you get understand that why the Finfet is used and why this technology has came in the market over the conventional or traditional MOSFET, right? So MOSFET technology, we know very basic of that because we have already studied the semiconductor technology, and including that we have already got understood that what are the basics of MOSFET, how the its working principle, and very basic parameters related to that, and by considering all the parameters, how to solve the problems and various problems, right? And we have already got an idea of the scaling of MOSFET, and that's a very exploration area of MOSFET in today's scenario, because we are at nano era, right? Because we are just at the moment we are standing at the nanotechnology situations. So this scaling is a very important part that we have already studied, how the scaling is done, and what are the scaling parameters, what are the related formulas, what are the parameters can be scaled using MOSFET, everything, right? But this FinFET is a very new technology that has been incorporated in your syllabus. This is the first time, and if you Google this FinFET, you will see some not at the undergraduate level. At the undergraduate level, there is no scope of studying this FinFET, right? But these concept has incorporated in your syllabus to get you understand, to get you updated that what technology are being used recently, right? And if you search in a Google platform, you will see that a very few research papers are there, and where the FinFET is being used as a research topic, right? And if you go through very detail, you will see that in IITs and ISC Bangalore, there the FinFET technology is used, and some and through MATLAB you can code the FinFET, and you can simulate the FinFET, and you can study, and you can do the research, and very few topics are there. So it is very upgrading and emerging research area at this moment using FinFET, right? So we need the very basic of FinFET, and so that we can say that yes, these are the challenging area where the FinFET is taking the whole control over the MOSFET technology, right? So this picture I already shared in the PDF, and that I have shared in my at the beginning point of my video lecture. And this is nothing but your silicon on insulator structure, that is SOI structure, and this is a substrate, there is a source, there is a drain. But there is one important thing, that this gate is wrapped, right? This is a wrapping structure of the gate, and here the two gate terminals are there. But normally we have studied till now that there is one gate terminal. So why there is a need of more than one gate terminals? But not only, I must mention that not only one gate, you can use 3 gate, you can use the all over gate structure, all around gate structure. Here is one, here is another one, here is another one, and here is the last one. So this structure is known as GAA structure, gate all around structure, right? This is a double gate structure. You can use a tri-gate structure, or you can use the all-around gate structure, that is GAA structure, right? But the biggest question is that why there is a need of using more than one gates, and this is the all about FinFET. Okay, so what is your why the significance of fin, right? Because we all know that in a fish there is a fin structure, and that's why I have compared with the structure of a fish, That's and this will give you a brief idea of this kind of structure. This is a wrapping structure, this is source, this is drain. So that's why it is known as your Finfet. So behind every nomenclature there is obviously a significance of that, and that's why I am sharing this is a fee structure to get you well understand the significance of the nomenclature, right? Okay, so just this moment my question is why this Finfet, right? This is the biggest question, why the Finfet? And after that we will enter into the detail of Finfet, right? Because there are various kind of effects as I shared. I think that some of you have gone through the PDF studies that I shared. There you must see that there is a short channel effect, long channel effect, DIBL effect, and this is a very important within quote, this DIBL effect, and that is drain induced barrier lowering effect. So how this effect is occurring and how the Finfet is used to reduce that effect. So that will be discussed in my today's video lecture, right? So stay tuned for that. And now coming to the very basic question that I have already asked, that why this Finfet? Okay, I am writing over here. I think it's visible. Yes, why this Finfet? This is a very biggest question, right? So before going to the Finfet, we need the our reference level, that where we were the MOSFET technology, we were the in-channel MOSFET, we know the P-channel MOSFET and everything, right? So let's take an example of your N-channel MOSFET and how it is done. A very basic structure that we have already shared. Tremendous time. This is N plus, this is N plus, and this is your oxide layer, this is your gate terminal, this is your source, and this is your drain, right? So this is a conventional traditional MOSFET structure that we have already studied, and this is the N-channel MOSFET because we are using the substrate of P-type, right? So before we move to the discussion point of technology and manufacturing of Finfet or tri-gate structure or gate all around structure, we need to get a brief motivation by which brief motivation why there is a need of this Finfet, right? So what is the need to move from this planar MOSFET, this is a planar MOSFET structure, to the Finfet structure, right? Okay, so if we look that in the normal MOSFET design, there is nothing but the source terminal, gate terminal, and your gate terminal. There is a substrate structure, and there is a channel, that means connecting region between source and drain. Why there is a channel and how this channel is formed? Obviously, this is the control over the gate. So gate has the all power to control the current conduction between source and drain terminal, right? So if we see the band structure, here I think it's visible. If we see the band structure of that, so this is your EC conduction band, this is your valence band, and this is source, and this is your drain, right? So this is the barrier, and this barrier is, this is the barrier. What barrier? Because from source to drain the current conduction will take place, right? And in a planar MOSFET, we will see that electrons see this barrier, but this reduces with the gate voltage, and electrons can control not control, electrons can flow from the source to drain, right? So whatever we can say, that I am just writing over here to get to understand, that is electrons see the barrier, but it reduces with gate voltage. It reduces with gate voltage, and electrons can flow from where? Current conduction flow from source to drain. I think up to this point there is no confusion, right? Okay, so again I am saying that if we see the band diagram, we are trying to find out that what will happen, what will happen if we apply some gate voltage, right? So whenever the gate voltage is applied, electrons will be attracted towards the channel. This is the main scenario. I'm again repeating, whenever the gate voltage is applied, electrons will be attracted towards this channel, right? And because of that, if we increase the gate voltage, the channel formation will be there, because this is under control of the gate voltage. I am again repeating, this is under control the gate voltage. That's why whenever the gate voltage will be increased, then the channel formation will be there, nothing else, right? Channel formation will be there. Now when we apply some drain voltage, this is the point, this is the beginning point, right? So whenever we apply the drain voltage, and because of that, there will be the conduction of the carriers from source to drain region, right? Because you are applying the drain voltage, so obviously there will be a conduction of the carriers from source to drain region. But if I suppose the carriers are coming from the substrate to source or the substrate to drain, we can't say that this is the current conduction, because current conduction means the carriers are moving from source to drain, nothing else. So if the carriers are coming from the substrate to source or substrate to drain, then we can't say that this is the current conduction. Okay, so if the gate voltage is absent, then the channel is absent, right? And if we apply the drain voltage, current conduction will not take place. Okay, so if we increase the drain voltage, there will be no change in the barrier potential, because it's all under the control of your gate voltage. I am again saying, if the gate voltage is absent, then the channel is absent, and if we apply the drain voltage, the current conduction will not take place, because we all know that this current conduction takes place under this voltage of the gate voltage. So if we increase the drain voltage, there will be no change in the barrier potential, because current conduction is all about is related to the barrier potential and everything that you have already studied in your previous semester in a solid state device and in your basic electronics part, right? So this is a very beginning section, that the control of the drain voltage. These point comes to the focus, that is this drain voltage, and because of this drain voltage, what will happen, what will occur, that will be seen in the next section, right? So we, up to this, we knew that the gate is all, that the gate has the all power to conduct the current from source to drain. But in my scenario, the drain voltage has entered, right? Just an unwanted person. So what effect of the drain voltage will be in the current conduction, and how that effect can be reduced, that will be discussed in my next section, and that is the basic significance, the basic beauty of the Finfet, right? But before going to that, I must give you some concept, some new concept, that is that you already know, I think. That is a long channel MOSFET and the short channel MOSFET, because we all know the short channel effect, because you have already I have already discussed the short channel effect in the scaling part, right? But here I will again discuss and again give you some brief idea and some new idea, and that will help you a lot in a competitive exam also, that concept, because this concept you I think that most of you don't know, right? So this is I will clear that thing, because I have taken this opportunity to discuss the Finfet, and related to Finfet I must say some important points that will help you a lot. But this is the beyond Finfet structure, because again I am saying that I am discussing the overall Finfet in very detail, right? In very detail, and that will help you a lot in later. But if you want to compress my lecture and as a short note of Finfet, you can do that, yes, but because for your semester it's not needed in detail. But I think that you should get the knowledge in detail of Finfet, and whenever you are studying this Finfet, the related process or related phenomena, phenomena, different phenomena related to Finfet you should know, right? So that's why I am delivering my lecture in detail, right? But you can compress it in your way. Okay, now this is a long channel MOSFET. Just write down the point. This is long channel MOSFET. Okay, you all know that this is long channel MOSFET. Okay, so if we want to draw, just a minute, if we want to draw these characteristics curve between your ID and VGS, right? ID and VGS, I will get something like that. I think that this graph I already shared, but I think that most of them have not understood that what is this. And this is your sub-threshold slope. I can take the slope also. I am writing this is sub-threshold slope, right? This is a very important point, but you should know in detail, and that's why I will discuss in detail, right? Okay, so let's move on. If we draw this ID versus VGS curve, then we can see that there is some exponential region and there is some linear region. Okay, and there is some sub-threshold slope. There is some sub-threshold slope. Okay, there is some sub-threshold slope, right? So if we change the drain voltage, the drain current increases in long channel MOSFET, and if drain current increases, then on and off current both increases. This is your off current and this is your on current, both increases. But from my perspective view, it's my question that do you know in detail that what is the sub-threshold slope, what is this on current, what is this off current, and what the effects of this on current and off current in your long channel MOSFET, right? So this thing will be clear first, that what is sub-threshold slope, because we all know that in the characteristics curve of ID versus VGS, there is some linear region, there is some exponential region, and there is some slope, and that slope becomes constant, remains constant, right? And remains constant, and related to that, if the drain current increases, then on and off current also increases. But we can control these on current and off current by using this slope, and that is how. So in order to get the answer of that, we should know very detailed that what is sub-threshold slope, right? Okay, so coming to this point, that what is sub-threshold slope, so just write down this. I think that you all know this, sorry, is visible. This is your IDS. VTH, right? This is a threshold voltage. Okay, so this from this linear characteristics curve, we all know that the current increases exponentially from the certain point, because I think that these threshold voltage concept you all have, because you have already solved the examples by considering the threshold voltage, right? And from the previous Google Meet, I think that you can also find out that what is the threshold voltage and what are the effect of threshold voltage in drain current and gate voltage consideration, and what are the formulas related to that. Okay, so you all have the concept of the threshold voltage. So from this curve, what is seen, that the current increases exponentially from the certain point, and which is called the threshold voltage of this MOSFET, right? But we can see that current below this point, right? So below this threshold voltage, What is that? Obviously this is 0, right? But this is the ideal. But practical, in actual reality, it is not 0. So how it will reflect? This will reduce exponentially. Okay, so I must say that the current which is below VTH, that is 0, but in reality it is not 0, and it reduces exponentially, right? It is reduces exponentially. So how it reduces? Let see the structure, how it reduces, and from that graph we will get the concept of subthreshold slope. Okay, so I am again just drawing this graph. So this is your simple VG, this is your IDS, because if we take the log curve, otherwise we can't see the slope of that. Okay, so if we take this structure, just pointing out, this is my VTH. If we point out that this is my VTH, obviously there is some on current, because we know that after VTH the current increases exponentially, and so this is my on current. This is I on. You all know Bode plot. I think in a control system you have the idea of that. So from that concept you can also relate how this graph is drawn, right? So this is your on current. So current above VTH is more or less is constant, and which is known as the on current. I will share the PDF also. Don't an issue. So current above VTH is more or less than constant, and that is known as your on current, right? But our consideration area is this portion, less than VTH, below VTH. So current at below VTH, which is in practical scenario, it falls exponentially. It falls exponentially with some slope, and that is the point. That is the point. This region, right? So at VG equal to 0 means this portion, right? There is some constant current. How we can relate this current? There is some constant current, right? But VG to 0, but there is still some current. Okay, and this term is known as your I off. This is the off current, right? So what is the term is used to explain this? This is the ratio, that is I on by I off. I on by I off. So if we assume that my on current is in the range of milliampere and off current is in the range of nanoampere, because it's a very less. So what is the your ratio becomes? This is milliampere means 10 to the power minus 3, and nanoampere means 10 to the power minus 9. So it's all about your 10 to the power 6. Got my point? It's all about your 10 to the power 6, right? But we can control this, and these the subthreshold slope. This is the subthreshold slope is does not change if we consider the low voltage with respect to your VTH, right? So if we consider this region, note it down. If we consider this region, okay, which is low voltage with respect to this, so my on current will be this section. This is my on current and this slope. So then off current becomes this one. Got my point, right? So then this off current increases, so obviously the overall ratio will nothing but decreases. Okay, so this curve, this subthreshold slope, or it also known as subthreshold curve, is a very important parameter, and we can get the less off current. So that's why I have mentioned the subthreshold slope, and where the totally your that remains constant. That remains constant, but it reflects, and it reflects a very important part, and it's a very important parameter through through which we can get less of current. And I must mention that the related formula of that, and what is the related formula? This is S equal to 61 plus CD by C ox. It's a higher standard formula, but you should know the formula. And this is your depletion capacitance, and this is the oxide capacitance. You all know that. In a scaling portion you have studied. This is the depletion capacitance and this is the oxide capacitance. Right? Okay. So I think that this will give an idea that what is the sub-threshold slope. Okay. So coming to my point, coming to this point. So what is the conclusion? That in the long channel MOSFET, if drain current increases in times, there is in time increase in the drain current in on and off states both. But the sub-threshold slope or the sub-threshold curve, that remains constant. Right? Okay. So coming to the another section that we have already studied, the short channel, but sorry, this long channel. But now we will consider this short channel effect. Right? This is a short channel effect, or we can say that this is short channel MOSFET. Okay, the short channel MOSFET. So first of all, I will draw some band structure, and that will give a clear idea that why FinFET is needed. This is EC, this is EV, this is source, and this is drain. And similarly, EC, EV, this is source, and this is drain. Okay. Okay. So coming to this point first. This is a two case study. Okay. At low drain voltage, whether because now we are coming to that point, that the drain voltage where we left, right? The drain voltage is coming to my scenario, and how this effect can be reduced using FinFET. So if drain voltage is very low, that is we are considering is 10 millivolt. Okay, so things are all same that of your long channel MOSFET, and barrier lowers with the gate voltage only, not an issue. So this is not a big problem, right? Because gate is controlling everything, so it will not create a big problem, right? Okay. Now, if the drain voltage is 1 volt, right? But so this is your high drain voltage, and because of that, barrier also lowers with the applied drain voltage, and this induces the main effect, that is drain induced barrier lowering. Got my point? So whenever the drain voltage is high, that means we are considering VD equal to 1 volt. So barrier lowers with this applied drain voltage. So drain is controlling, drain voltage is controlling, and these will create an effect that is known as drain induced barrier lowering. It's a very important point, very important parameter. Right? So this is a very big problem, because drain is taking the control from the gate, and this means that the barrier from electron, the barrier for the electrons to flow from source to drain is not only affected by the gate voltage, but also by my drain voltage. Right? So from this kind of discussion, what is my conclusion? So please listen very carefully, that whenever the gate voltage is 0, that we have already discussed previously, there is no current, right? But because of this smaller channel, if we apply the drain voltage, still there is a current. But that current we must consider that this is a leakage current, and this is the undesirable characteristics. But barrier for electrons to flow from source to drain is not only affected by the gate voltage, but also affected by the drain voltage, and that is creating this kind of effect which is known as drain induced barrier lowering effect, and this thing is totally undesirable. right? So what is the way out to get rid of this effect, right? So what is the possible option? What is the possible option? So one thing I must highlight it, that from this kind of discussion, what are the drawbacks? The first drawback is DIBL, and the second drawback is subthreshold voltage. Subthreshold voltage changes. Subthreshold voltage changes, and the third one is your off current increases. Okay, so what is my possible option to get rid of everything, right? So as we have seen that the short channel effects are bad for the devices and the circuits, but because why this is the bad for all devices and circuits? Because these effects are lowering the gate control over this current flow. So this is our main point, because this is this reduces the control of gate in the case of the current conduction from source to drain, right? So what is our way out? My way out is, if we add one more gate, okay, one above, one below, and that is a double gate MOSFET, or also put the gate in the side also, that is a tri-gate MOSFET, or put the gate all around, that is GAA structure, then the control over the current flow can be increased, right? So my question is, what is the way out? So if we add extra gate structure, then we can get rid of the everything. And I must say that how this is seen, I have drawn the structure of that. This is your structure. This is your all about structure. So this is the wrapping. This is a double gate structure. This is source, this is drain, and everything. So I will share this structure. Not an issue. Okay. So let's come to the very briefly that how it's working and what are the challenging areas, and how the Finfet has accepted the challenges to execute properly, right? To execute the or to get back all the control of the gate. Now, what is my point? So I must say that these Finfet, this is an emerging technology. This is an emerging technology as a replacement for traditional MOSFET. As a replacement of what? This traditional MOSFET. Traditional MOSFET, right? Due to their better performance in the subthreshold region. I will share the PDF, right? So this is first point. What is my second point? The lowering of the leakage current and improve this on-off current ratio in this quasi-planar structure over the MOSFET. So this is also done by the Finfet. So what is done? This is lowering, that one of the major drawback. This is lowering of leakage current and improved on-off current ratio, right? So this is this was one of the major drawback whenever we discuss in a conventional MOSFET, right? Okay, so what is my third one? My third one is being compatible with CMOS technology, because in my nanoscience I will prefer the CMOS technology that I have already shared, right? So being compatible with CMOS technology, with a few additional fabrication steps further enhances the chances of Finfet becoming the state of art in semiconductor technology. Okay, so my third point is these Finfet in today's scenario becoming the state of art, in where in semiconductor technology, due to what? Due to its what I can say, due to very simple fabrication process. Fabrication means how this IC is formed, this integrated circuit. There are various kind of steps. Due to this simple fabrication process in CMOS technology. right? Okay, so this is my third and important point. And what my fourth point? The power consumption in the transistor occur mainly due to the switching action and leakage. That is also overcome in this section. And the technology scaling results in tremendous increase in the leakage power component. So scaling is very much friendly. So all other parameters associated with FinFET is a very good sign to use this FinFET over the conventional MOSFET. Okay, so to design our devices with reduced leakage and your minimum delay at the same time requires the scaling of operating voltage as well as the gate sizing. So this is all, these all are expected from this FinFET. Okay, so I must say the point, that is reduced leakage current, minimum delay, that's our the requirement, right? Minimum delay and scaling of operating voltage as well as gate sizing. All are done in FinFET. Okay, so presence of multiple gates open the scope for various modes of operation in FinFET based circuits. Obviously this is done, right, because this is the presence of multiple gates and it's a very important feature over this conventional MOSFET. So due to these several advantages, we can say that this FinFET is chosen as a proper replacement of MOSFET. Clear? And lastly, I must say a few points, that is what are the important key features of your FinFET. What are the important key features of your FinFET? So this is your FinFET structure, right? And major challenge faced in scaling of MOSFET are the sub-threshold leakage and the drain-induced barrier lowering, and which are the effects of reduction in the channel length, right? And FinFET as a variant of the MOSFET is a planar structure, and where the source and drain regions are grown over the layer of insulator. And this device gets the name from the fact that the conducting channel wraps around this fin. The device gets its name. Again, I am saying that the device gets its name from the fact that the conducting channel wraps around this fin. As I have already said, and hence is often called. I have also mentioned this SOI device. This means the silicon on insulator devices, right? So from this structure, it is very clear. And lastly, I can say that the channel connecting the source and drain region are usually called the fin. And the fin parameters, just like your fin height or the fin thickness means this one play a very key role in the operational characteristics of the device. Okay, so device can have one or more multiple fin. Fin means the gate, nothing else. The device current increases for n fin devices. So I must say the device current increases for n fin device, right? So this is your all about FinFET. I think that it will give a very clear structure and it will clarify many doubts if you go through this video lecture very carefully. And again, I am saying that in your semester, I think that this will be coming as a short note or in a group B question as a marks of 5. So please try to compress my video lecture. Please make a short note that I have already shared from the previously shared PDFs. Please try to reduce these notes as your short note. Okay, so this is one of your assignment to reduce in a short note from my given video lecture or my given PDFs, and please go through that. Okay, thank you so much.